Hi, good morning. This is Jagdish, Assistant Professor of EC Department, SNS College of Technology, Coimbatore. And today, in our video lecture series, we are going to discuss the planar power MOSFET. This topic comes under the Unit 2, that is switching characteristics of WBG wide bandgap devices. Come, let's get into the topic. So, planar power MOSFET. So, before getting into the planar power MOSFET, we must know what is MOSFET. So, MOSFET is nothing but of metal oxide semiconductor field effect transistor. So the metal oxide semiconductor field effect transistor, which has three terminals, one is a gate, source, and a drain. There are two types: N-channel MOSFET and the another one is a P-channel MOSFET. Based on the channel variation, it has been classified into two types: N-channel and the P-channel. So the source to drain current flowing that will be controlled by the gate terminal. And this is the planar power MOSFET. This is the physical structure of planar power MOSFET, where the number one pin is called as a gate, and this is the two drain, and the third is a source. And a planar power MOSFET, which is used in many applications, in audio applications, power amplifier like that. So this is here you can see the planar power MOSFET, which is fixed on the PCB. So planar power MOSFET, as I said, it is used in television, radio, laptop, SMPS, and UPS, then DC motor for speed control and on and off cases. So here you can see in this image, these are all the power MOSFETs, planar power MOSFETs. So planar power MOSFET, it is a voltage controlled device because of the gate voltage, the source to drain current will be controlled. So it is a voltage controlled device. So here you can see that's a P substrate is there and the N channel and a drain is there. That's a D and source and gate terminal. So the gate terminal to the substrate, which is in between, we have a SiO2 layer is there. So it is a simplified structure of power MOSFET. It is a four-layer device, that is N plus, P, N minus, and N plus. Three junctions is there. That is a J1, J2, and J3. And three terminals, that is a gate, drain, and source, that we know already. So this is the basic structure of N-channel DMOS power MOSFET. Here we have VDD, load is there, and VGS is there, then source is there, and drain, source, drain, and it's a gate. And here we have a drift region for P-type and N plus substrate, and metal layer is there, and this is a current path. And silicon dioxide metal is placed over on the structure. So this is also the current flow is indicated by the red line. So it is also the planar power MOSFET structure, and this is the device characteristics. So it's a device characteristics is plotted between drain voltage and for drain current. Drain voltage, and drain current is mentioned by the ampere, and increasing gate bias. By increasing the gate voltage, we have the characteristics is getting increased. That means it is increasing. So the power MOSFET characteristics in the first quarter at the low drain bias voltage, and this is the first quadrant at high drain bias voltage is given over here. Device characteristics, that is a useful parameter that is commonly used for describing the operation of the power MOSFET structure, is its transconductance. The transconductance is defined as the rate of change in the drain current, which is incremental gate voltage. That is transconductance, that is defined by GM, that is delta ID by delta VG, which is nothing but of ID4 minus ID3 by VG4 minus VG3. Device characteristics, that is a power MOSFET characteristics in the third quadrant at a low drain bias voltage. So what is blocking voltage? The power MOSFET structure is capable of supporting a high voltage in the first quadrant of the operation when the drain bias voltage is positive. During the operation in the blocking mode, the gate electrode is shorted to the source electrode by the external gate bias circuit. So it is the depletion layer with the P base region of the power MOSFET structure is given in this characteristics. And a breakdown voltage for the power VD MOSFET structure is given here. Forward conduction characteristics. On-state current flow can be induced in the N-channel power MOSFET structure by the application of positive gate bias to create the channel extending from the N plus source region to the N minus drift region. At the drain bias voltage that are small when compared with the gate bias voltage, the characteristics of the power MOSFET resemble those of a resistor whose magnitude can be controlled by the gate bias. So forward conduction, when the drain bias voltage become comparable to the gate bias voltage, the resistance to the current flow increases because the drain bias counteracts the gate bias voltage. The IV characteristics of the power MOSFET structure are governed by the behavior of the channel region as a function of the gate and drain bias voltage. The low on-state resistance of the power MOSFET structure, it is most important attribute for the power electronic applications. In conjunction with the inherent fast switching capability, this property of power MOSFET structure enables maintaining low power losses in the applications. The impact of the device cell topology must be taken into account during the computation of the on resistance. Forward conduction occurs when a positive bias is applied to the anode with respect to the cathode with the positive voltage gate voltage greater than the applied threshold voltage. Current flow from anode to cathode must pass through a PN junction formed by the P plus substrate and the N minus drift region and the MOS channel. Why are power MOSFET are used? The power MOSFET are used to control high current or power in the circuits. These are often single transistor packaged as a discrete components. These are common in switching, power supplies, and motor controllers. Thank you.